Hello, everybody. My name is Shamik Ghosh, and I'm the CTO of Medius Health. The topic of my presentation today is using AI-driven lab test analytics for digital transformation of health risk prediction workflows. Here follows an outline of the presentation. I'll start with the background, give a problem description, a proposed framework of the solution, our insights and conclusion, and then a demo from a partner. So what's the background here? Typically, laboratory reports from diagnostic labs cannot necessarily be interpreted until they are actually analyzed by human medical experts. This means that immediate interpretation of laboratory reports is not possible, and there doesn't exist currently systems that can automate such analysis. As part of their regular day-to-day workflows, clinicians have to go through multiple lab report analysis in numerous non-critical situations. For example, medical checkups. A situation like this, typically because of unavailability of automated systems, the stress on these systems, these medical systems, can be a lot. Further, the user doesn't necessarily get a very solid, insightful report about what kind of potential conditions or what kind of prediction could be possible out of the lab report analysis. For us, Medius Health, the problem description was almost on the lines of the unavailability of actual examination, automated examination of these lab reports in the current state of the art. A number of diagnostic labs today provide manual examination of these reports, and that introduces a certain level of operational inefficiency within the medical system. In use cases such as medical checkups, these kinds of examinations can be very tedious and they can cause a lot of human errors. Further, this introduces longer feedback times on the patient's side because GPs need to have time or get time to make sense of the lab reports. Storage of such lab reports as PDF files or manual translation of these files to be stored into databases is also a time-consuming and a very inefficient process. Further, while a medical professional goes through and manually analyzes this report, there might be errors that can be also introduced. The possibility of an automated system is paramount in these kinds of situations. Our proposed framework consists of the construction of a large-scale lab test knowledge graph for real-time report processing. In this knowledge graph, there exist nodes and edges. Nodes typically represent lab test entities and disease entities. Edges can be relationships between these lab tests and diseases. Lab tests and the values in diagnostic lab report are detected using a lab test entity recognition model that has been developed in-house and reported upon by Medius Health. The recognition model typically goes ahead and, apart from detecting lab test entities, also detects reference intervals, mentions of units, and actual values for the patient lab tests. Detected lab entities are then mapped to the Medius knowledge graph using entity linking algorithms, which are dependent on deep embedding models based on natural language processing algorithms. Once these lab tests and their associated values and units are recognized by our knowledge graph, we detect which specific lab tests have anomalies in this kind of a scenario. Further, we use the lab test with anomalies to perform a walk through the knowledge graph and then predict the most relevant conditions and diseases. The image or the diagram in front of you describes a very small section of the diabetes portion of the knowledge graph. As can be seen, the HPAC lab test entity can be connected to something like pre-diabetes, diabetes, and uncontrolled diabetes using various relationships. And these relationships have properties. These properties encode reference intervals. Further, once the knowledge graph is built, when a free text in a lab report is identified, at that time, we extract using certain pattern extraction algorithms the actual lines within a table in a lab test report. Using the concept of entity disambiguation in LNP, we try to obtain mentions or we detect terms and tokens within the sentence to ultimately build out and connect these words to the specific lab entity inside this knowledge graph. So what happens typically is there exists a meta graph of words and mentions of text and tokens within a sentence, and they are finally getting mapped to a specific real-time lab test entity inside the knowledge graph. The lab test reference intervals, values, and units are then detected also using some of these patterns. Once they are detected, we use the knowledge base to verify if the reference interval in the lab report overlap with those in the knowledge base. This also means that we don't necessarily have to be dependent on potentially faulty uh, reference intervals, and or even be dependent on reference intervals which could differ in different countries. The units are also cross-verified to check if detected units are valid units. In many cases, depending on which diagnostic lab we are talking about, the units of lab test values could differ. And these are associated with the detected lab test. The result typically comes out in the form of the example as given below. Here, what happens is the image gives you an idea about how a lab test is then um, mapped or walked through the knowledge graph. So we check first if there's any value for the detected lab test that is falling outside the range. If this value has fallen outside the range, then we walk through the graph and select the specific disease. After all the lab tests with anomalies and the corresponding diseases are detected, we generate a personalized graph, which is very specific to this particular patient based on the lab test and the corresponding diseases. The personalized graph, which is very specific to the user, to the patient in this case, the nodes, the subgraph for the nodes, the edge weights are used then to finally rank and obtain a proper ranking of the diseases. Here, we also eliminate finally the diseases that are ranked the lowest. As part of our insights, what we noticed was when deployed at an initial level of an MVP with our partners, we noticed that this kind of a report analysis framework was able to analyze reports in few minutes. We were able to provide better insights, faster insights to the medical professional, and that aided in decision making for the medical professional. Further, we smoothened out the process of storage of these lab reports to a great degree, and we were able to map the specific mentions and terms in a specific graph, which was also stored on the customer's end. Uh, Finally, we helped in the reduction of stress on these kinds of medical systems by automation of the analysis of lab reports. At an industrial level, diagnostic labs tend to be third parties that work with a number of healthcare organizations, whether providers and payers, to who these services are provided. As a result, the operational inefficiency creeps in due to a lot of manual work that is involved in the analysis of a lab report. Instead, Medius Health proposes this solution where a lab test analytics workbench and our specific APIs could be used to automate the analysis of the lab test from end to end, and have the report easily in a few minutes in front of the doctor for analysis. Next, we provide a quick demonstration uh, of the lab test here, of the lab test workbench here. As you can see, um, what we do here is initially browse the specific lab test report. In this case, the lab test report that we have used is one of our partners, and sections which have PII have been reducted here. And as you can see, again, it goes through a number of biochemistry and other kinds of lab-related reports about this particular user. And then um, following that, there's a component of the text extraction which goes ahead and uses OCR to read the entire report. Once this report is read, we upload the report, and the report starts getting processed. This entire process typically takes around 2 minutes, but ultimately it generates the necessary results that we need. As you can see here, as part of the API call, what we have now generated or we have extracted is the entire text that is required for us to be processed. This component involved a fair amount of data engineering on our side, and you can see a lot of garbled reports also come out in these kinds of scenarios. In the next step, we have detected reference intervals, units, and values, which are also extracted from the text. One of the important factors here are we go ahead and we are able to put a well-defined structure to the text that was extracted. This image shows the mention detections part from the text and how entity linking is being performed within the graph. So what you can see are different parts of the graph which are being detected based on the text which has been obtained here. Following from there, you can see as part of the final report, what we have is the Medius ID of that particular lab test, the Medius name of the lab test, the mentions that were captured by the lab test, the confidence of the mention and its correspondence with the actual lab test entity, the value, the unit, the detected reference intervals, and the status. You can see the anomalies being marked as high. In certain cases where the lab test value is normal, we show what the lab test value is. And then finally, at the end, you get a report about the predicted diseases. In this case, what we show is the score. The score is the actual example or the detection of how good the lab test detection is, or what the diseases are, which are the best diseases in this particular situation. This was an implementation which was performed with our partner, and this is currently in operation with our partner, one of our diagnostic lab reports partner, to whom we have provided our medical chatbots also for usage. Thank you so much. Questions?